The road to IPv6. I'm ready. I just had a conversation with one of the network technicians I work with, and we were trying to figure out new subnets for a school, actually, that we do some network support for. And he goes, things are just getting bigger and bigger. Everybody walks in, they've got iPads, tablets, iPhones, Androids, blah, blah, blah. They're just walking devices all around the campus. And our little /24 subnets don't hold them anymore. We started having to use /23 and even in one case, a /22 mask. And so we're trying to figure out how to scale this, how to make this work for a lot of our other customers. And I go, this is just writing on the wall. It's only so long, even on the private IP addressing side, as we're going through this model, that we can keep up with this before we just tap out the private pools. I said, we need IPv6. And he goes, oh, are you saying? And I said, no, I'm not saying that we're going to roll out IPv6. I'm just saying that the reality is the internet is not getting any smaller. Devices on networks are growing more and more and more. Everything's got an IP address. That's why they're now calling it the Internet of Things. If you haven't heard that before, go Google Internet of Things, and you'll just see all kinds of stuff that is now connected and online. So IPv6 is the solution. The question is, how do we get there? That's the core of this nugget, is talking about how do we move from this IPv4 world that we're in to IPv6. Here are your do I know this already questions, so skim those questions. If you know the answers, move right along. Well, I went on a fun Google fact-finding session on just how big is the internet. Now, I'm midway into the year 2014. I couldn't really find any stats for where I'm at right now, or even 2013, but they must have launched a research project in 2012 because there's a lot of stats out there. So take a look at this. From 2007 to 2012, we went from 1.15 to 2.27 billion internet users. Billion internet users that are out there. Just crazy kind of growth. Now, it's funny, I looked at this picture and I thought, I'm here in North America. I'm like, well, that's not that big. And then I realized, oh, well, that's because the internet started here in North America. The United States pioneered this thing we now call the internet, which is now spreading worldwide. Look at this. Look at Latin America, 110 million to 236 million, more than doubling. We've got Africa. Oh, my goodness, look at this. 34 million to 140 million. Ironically, I was just talking about 2 weeks ago to a guy at my church who just got back from a mission trip in Africa. And he said, Jeremy, you would not believe the amount of people that have smartphones out there. And he said, that's how they're getting online, is a lot of the smartphone technology. That's like the way. And I thought, wow, so I put a little fact on there. Mobile technology, 63% of all cell phone users go online with their device. I mean, good grief. It's become ingrained. When I travel, which I do every now and then, I love just doing people analysis. And you'll see people like, I sat next to this person on a plane, and she had an iPad. And it's funny because we sat down on the plane, bling, you got to put away your mobile devices with it. So she puts the iPad under the thing, and then bling, it comes online. And then she opens the iPad and looks at it. Why? Because she had no reason to open the iPad other than the fact that is what she had trained herself to do. So I watched her. I love watching people and just kind of analyzing their psyche. And so she's like, okay, she's kind of flipping through the pages of apps, and she's like, oh. And so she looks at this app, and then after about 5 minutes, she closes it, and then she kind of sits there and stares for a while, and then she opens it back up, and it's almost like this weird cyclical cycle where, again, she opened it. It's almost like Pavlov's dogs, right? She's trained herself to just be like, I don't know what to do. Oh, look, boom. She opens it, and she's like, surf, surf, surf. Oh, I'm going to go into solitaire. And she plays solitaire for 2 minutes, gets bored with it, closes it again. And the funny thing, I'd like to say that's isolated to just that gal I'm sitting next to on the plane, but it's a pandemic. You look around the world, and when people hit idle moments in their thought, what do? Bam, they pull out their mobile device, they look at it, they don't know what they're there for, but soon they're going online. So mobile technology is fueling a lot of this internet traffic just because you're always there, always connected, always communicating, over-communicating in what I believe. But anyhow, I just get on my soapbox for a moment. So public IPv4 addresses are gone. We're running shorter and shorter and shorter on these things. It is exhaustion imminent to the point, like right now in the United States, you get a public address at your house. When you bring up a DSL cable modem connection, you can usually go out there and see that you have a public address unless you're in a real rural area or something, a small ISP. But that's not going to become the norm. And outside of the United States, that's not the norm. Talk to many people outside the United States, and they get private addresses. People in Asia, the service providers doing NAT from the home to NAT inside to NAT on the out. I mean, there's many layers of NAT. We'll talk about that in just a moment. So service providers are very motivated. The world is very motivated to move to IPv6 because we've reached the end. IPv4 can only stretch so much further as this growth continues. So I'm planning on camping out on this slide for likely the rest of the nugget as we talk about how do we get there? What are the different solutions at our disposal? Because different service providers will make the move at different times. You can't have this worldwide coordinated effort. Okay, on June 3rd, 2018, click, we all push a button and boom, we're sitting there on IPv6. It's going to be a gradual stage thing so that we have to have kind of this translation time in the middle where we're moving from IPv4 to IPv6, and I could see it staying that way for quite some time. So let me hit some of these methods. I'm going to start off actually at the bottom. I'll kind of jump around here with NAT 444. What is this? Okay, method number one on how we get there is by a band-aid, a kind of in-between, if you will, that service providers can use to overload an already overloaded IPv4 network. See, a lot of times this is where we're at, where IPv6 internet it's a reality, it's there, but a lot of service providers haven't gone there yet. A lot of customers aren't even thinking about IPv6. They're running their cookie making business or whatever they're doing. So IPv6 is just not even a thought in their mind. Well, meanwhile, all of the internet routers are running out of public IP addresses. You have service providers that just can't get enough to feed to their customers. So NAT 444 becomes the solutions. What you end up with is the customer premise equipment, so this, just think of this as customer. Could be a house, could be a business, could be anything that is assigned a private IP address. Now, in like I was saying just previously, in the United States, that's not normal. Outside the United States, I have seen that quite a bit, where service providers are doing that. So private IP addressing is used throughout the ISP core, and a small set of public IP addresses are put right here on these edge routers. Now, I should say this edge router, just assuming there's no IPv6 internet there as of yet. So what is this CGN? What does that mean? That stands for Carrier Grade NAT. You might stick that acronym in your memory banks. Carrier Grade NAT. It's a router beefy enough to start doing a ton of NAT, because if you think about it, these routers are pretty overloaded themselves, just having one private IP address, and we're natting for 100 different devices behind the scenes. They're trying to keep up doing all these translations. Well, imagine a router doing that for not 100 devices, but 1,000 devices that are doing NAT behind it. So you've got just tons of traffic, tons of NAT ports that are being used up. Essentially, the goal is to stretch these public IPv4 addresses as far as they can go. That's NAT 444. Next method to get there, dual stack or DS Lite. I know I'm jumping all around, right? Well, dual stack is where you have the service provider and the customer run both IPv4 and IPv6. Now, I'm using this diagram for all these different examples, so sometimes I'll cross out one or the other, but dual stack really means dual. I'm running both. So as a service provider, you might assign the customer statically or dynamically an IPv4 address and an IPv6 address, right? And this could be public or private, because you could be doing the NAT 444, or maybe you've got IPv4 addresses to spare. So the customers, sitting out here, have their clients configured dual stack IPv4 and IPv6 addresses assigned to them. And what do? They surf the net. They try and access resources, and they do DNS lookups. Now, DNS, let me actually bring up a command prompt. DNS can get two different kinds of records. You can end up with a record, stands for an address record, which is the IPv4 address of a destination, or the AAAA record, which is actually the IPv6 address of the destination. Let me show you this. Do an NS lookup, right? Just to do a DNS lookup, I'm at 4.2.2.2. Let's just do google.com, right? And you can see that we've got two different kinds of answers coming back. It says addresses, this being an IPv6 address. So if the host supports and prefers IPv6, it's going to be like, bam, I got it. I'm going to use IPv6. Oh, bam, bounce, firewall of a command prompt. No, but it's going to go via IPv6 to the IPv6 internet and end up reaching Google's website over there, right? Or if it gets IPv4, maybe it either prefers the IPv4, or maybe you got a site like Nabisco.com, which I could probably pick just about any site in the world today, and I shouldn't say any, but the vast majority of sites in the world today, and it's only going to return an IPv4 or an A record back to the client. So he's going to go, okay, I'm going to just go on the IPv4 direction in that sense. Now, notice I haven't done this, so let's see if it works. Set type equals A. Let's do google.com again. Yeah, see, so notice A records just return the IPv4 addresses, but if I hit the up arrow and let's do set type AAAA and look up google.com, hey, there we go. We've got the IPv6 record that comes back to us. So you can see the difference. DNS controlling a lot of times the answer you get and the direction you go along with protocols that you prefer. Now, what's the scoop with DS Lite? DS Lite is pretty cool because it's kind of an in-between, if you will. So let's say the ISP has decided, okay, we are eliminating our IPv4 core, or we're going to minimize that because we've run out of IPv4 addresses. What they can do is start assigning IPv6 addresses to all the customer premise equipment, right? So global IPv6 addresses are assigned here, which are plentiful. There's tons of those. Customer still being IPv4, running their little private address world back here, right? So this router becomes a DS Lite router. And what happens is when the IP addresses, or I should say the hosts inside, go out, instead of doing just straight up NAT, trying to do like a NAT from IPv4 to IPv6, DS Lite allows you to encapsulate the IPv4 packet inside of the IPv6 packet, right? So that travels through the IPv6 core of the ISP, and if it's accessing something on the IPv6 internet, boom, it goes out, right? Because it's using just this embedded IPv4 address in there that, we'll say google.com out here running IPv6 doesn't care. It just sees a source address, right? So it comes back here, and the carrier can then route it back, and hey, we essentially went native IPv6 the whole way, and I'm doing, quotes around native, kind of, because the customer is still on IPv4, but we access the IPv6 internet. We didn't have to do any kind of NAT. Now, if the customer comes out and it realizes it has to reach something on the IPv4 internet, then the carrier routes it up here and essentially takes off the IPv6 outside and then does the carrier grade NAT and sends it out on one of the IPv4 addresses that it's NATing for all of its customers. So it's kind of a little hybrid between NAT 444 and kind of a new way, which allows the service provider to migrate to IPv6 without requiring all of its customers to be there as well, or building this parallel IPv4 network that it has to maintain and support. Now, remember, I'm talking about all these methods. And these methods are a variety. I mean, a carrier, a service provider, will start looking at this and saying, okay, well, what cocktail of methods can we put together to make the move to IPv6 while still supporting customers that choose to stay on IPv4? All right, now let's jump up to NAT64 and DNS64. This is pretty cool. So let's say we fast forward a number of years, and the majority of customers, or we'll just say our customers, are IPv6. We, as the service provider, have converted our core to IPv6, but there's still slow adopters out there, right? The world is a big place, and it's going to be a long time before all the devices connected to the current IPv4 internet go away and make the switch to IPv6. Okay, so what happens? Well, what happens is the customer, well, let's just say accessing a server out here, nothing, right? There is no need for this because we have a customer using native IPv6 the whole way through to access that device. But what happens when we have a slow adopter? We'll say Bob's Crab Shack, which sells crabs online to people. Bob's Crab Shack, which is 1.1.1.1 out on the internet, never converted their web server to IPv6. So we have this guy right here who does a DNS lookup. Let's just put the DNS server. I'll put DNS64, and I'll show you why in just a second. Does a DNS lookup and says, I'm trying to go to bobcrab.com. What is that? DNS server realizes, oh, there's only an A record, which is what? The the IPv4 version, right? And it goes, no, 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 we're running IPv6 everywhere. This can't be. So what it will do, and this is the DNS64 part, is translate that A record into an AAA record, right? Because think about it. When we move to IPv6, IPv6 has no idea what an IPv4 address is. I know that's weird. I mean, that sounds kind of funny to be like, well, of course it does. No, it doesn't. IPv6 is a protocol. It's not smart. It doesn't go, oh, you mean 1.1.1 is slash, 24, 28, whatever, 32-bit. Oh, I get it. That's the old version. No, no, no. IPv6 is IPv6. It speaks to things with a 128-bit addressing. It speaks to big old packets. It has all of these new features with IPv6. So if it gets an A response, it's going to be like, what? What's it talking about? Like, it doesn't know. It's not IPv4. So you're like, where are you going? So here's what happens. The DNS64 translates this A record into an AAA. Here's how. It uses either, the service router can designate their own little prefix, or it can use the well-known prefix of 64 colon FF9B /96. Now, what does this mean? It means it starts with 64 FF9B colon meaning all zeros up to the last. So 128-bit addressing, right? There's 96 bits. How many is missing? 32, right? So what it does is take whatever the IP address is in that A record, 111 in this case, converts it to its hexadecimal equivalent and fills in the rest. So the response it gives to the client, which is running IPv6, is, oh yeah, we've got 64 colon FF9B colon, and then whatever the hex equivalent is of 1.1.1.1 that I can't tell you off the top of my head as the DNS response. So this client is like, oh, great, that's fantastic. Sends it through. This ISP is smart and is running NAT64. So they recognize, oh, this is a translated address. You go that away, right? So this is where NAT64 comes into place, where it takes the IPv6 stuff and converts it to an IPv4 address. That's kind of a NAT way, right? Now, there's two different kinds. You can do stateless or stateful NAT64. Stateless NAT64 means that it does a one-to-one translation. So it's got a whole bunch of public IPv4 addresses associated with this router, and let's just say it's got, let's just say 5.1.1.1, 5.2.2.2. I know that's probably not the best way to add it up, but 5.1.1.3, 4, 5, 6, all the way down, it's got all these. So as this request comes through, it goes out as 5111 and reaches Bob's Crab Shack at 1111 and does it straight back. Now, while it's doing that, stateless means it's a one-to-one. So you don't conserve IPv4 addresses right here, but the benefit of stateless is it's not NAT, meaning you can do a trace route and see the full end-to-end connectivity. You can see the original host that requested this all the way through. You're not doing a high overhead operation on the router like NAT, trying to fill up your memory, doing all this kind of stuff. So in the end, stateless is actually better because it doesn't have to track the state of NAT. It just says, okay, I went from this IP address to this IP address, and then it comes back again. However, being that IPv4 shortages are what they are, we'll probably do mostly stateful NAT. Stateful NAT64, which is where we take 5111 and overload it for a whole bunch of IPv6 clients, and you lose the end-to-end traceability. You have higher overhead on the router, but all that in return, you get a huge conservation of IP addresses. Next up in the list, GRE or 6-in-4 static tunnels. These are pretty basic. If you've ever gone onto a Cisco router and configured GRE, it's very easy. Generic route encapsulation is the fastest way to create, I'll say, what most people see as a VPN on the fly. You essentially say, I've got, just for grins, let's say I've got gig 0/1 right here and gig 0/2 over on this side, right? Doesn't matter the interfaces, but all this stuff in between. I mean, you've got routers, switch, core, blah, 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 all this stuff in between. Well, what I can do with GRE is define a tunnel endpoint just with my source IP address, whatever's assigned here, and a tunnel endpoint on the other side with the destination address, and it literally just takes whatever traffic is coming, well, I'll say whatever I want, whatever I designate. It could be this customer traffic, and sends it through that tunnel. So essentially, it's never seen by the carrier network, and they never see any IP addresses in the carrier network because they kind of live in that tunnel through to the other side. Now, generic route encapsulation doesn't do any kind of encryption, although you could add encryption to it. It just tunnels packets. So you hide, essentially, the visibility. If you do a trace route from the customer perspective, they're like, hop, hop, they could go through all kinds of packets in between, but hop, and then bam, they land over here. They don't see any stuff because they're going through a tunnel with blinders up. That's the best way to think about it. Well, that's one way of doing it, as well as 6 and 4 static tunnels. So essentially exactly the same thing. Right? It's just they came up with a name for 6 and 4. A lot of times Cisco will implement 6 and 4 by allowing you to configure GRE. You actually go in and do interface, tunnel 0, give it a source, give it a destination address for the tunnel, and you actually then go, I think the command is encapsulation 6 in 4. And you hit the enter key, and now you're doing a quote-unquote 6 and 4 static tunnel. Right? So really these are the same thing. I don't want to say the problem with them, because it's not a problem. It's how they're designed, is they are static. Meaning, now remember, we are a carrier. A lot of times we get this ISP, an emphasis on the I, internet service provider mindset, and we think, oh yeah, we provide internet access. Well, service providers do a lot more, so maybe we're just connecting this customer to this customer. They are running IPv4, and we are running IPv6 because we made the jump and the conversion between. Well, how do we get them through? Well, that's where you could do like a 6 and 4 static tunnel, or it goes, I just went completely the opposite way, but you get the idea. We could have customers doing IPv6. Let's go that route. IPv6 on each side, and we as the carrier haven't converted our core yet, so we only do IPv4. So 6 and 4 means essentially the IPv6 address arrives right here, source and destination, and it tunnels it through an IPv4 network that's not seen. Challenge is we have to tack those up for every single customer that we have, every single endpoint, making the automatic tunnels a lot more attractive. All right, let's hit these last two, 6 to 4 or 6RD automatic tunnels. As you might have guessed, this benefit is the ability to build tunnels automatically versus the static configuration we just talked about. 6 to 4 means that the customer is essentially moved over to the IPv6 world. The ISP is still in the IPv4 world because customers may be ahead of the game. They may be wanting to do this before the ISP has a chance to convert all their equipment, whatever, right? We assign the customer premise equipment an IPv4 address. Let's just say it's 209.168.201.1, right? And over here we might assign them 209.151.1.1, right? Okay, so we give the customer premise equipment these public addresses, and this is configured then to do 6 to 4. Now, first thing that tells me is it's probably a managed router by the service provider. The customer doesn't manage it because 6 to 4 is not a common feature set in most customer premise equipment. But that aside, the customer is then required to assign prefixes of 2002 colon and then the hex version of the public IP version 4 addresses to their network. So 6 to 4 actually uses the well-known, meaning it's defined in RFC standards, prefix 2002 colon colon, right? The next 32 bits of that, that'd be 32, end up being the hex equivalent of this. Now, I chose this address. You might be like, Jeremy, you usually use addresses like 1.1.1. Why'd you use that? Because I figured out the hexadecimal version of it. So it will actually become 2002 colon D, hang on, I wrote it, D1A5 colon D1A5 C901. Got another monitor over there. By the way, you can just go and Google and type in IPv4 to hex conversion. There's a million tools out there on the web to do that. And then we'll do colon colon /48. So that then defines the network internally. So they assign addresses to their internal clients based on that. Now, when this customer premise equipment realizes, let's just say we've got a host in this subnet, and it's trying to communicate with another island on the IPv6, what it will do is use whatever this is, because 6 to 4 recognizes it as the public IP address, and embed this address inside the packet. It'll then send it to the other endpoint across the IPv4 network. Now remember, this guy's communicating via IPv6, so the customer premise just looks at its destination address, which will be 2002 colon whatever this is. I didn't figure that one out in hex, right? So hex. So when this guy says, okay, I'm coming from this source, which is whatever address he has in that subnet, going to the destination of whatever this prefix is, customer premise equipment is like, oh, this is a 6 and 4 destination. So I will extract this essentially from here and make it the destination IPv4 address. I will extract this right here. Well, doesn't really have to extract because that's going to be the source address assigned right here on the public interface, right? And then it sends it across. Now, when this guy gets it, he looks at the packet because it will take these and embed them inside the packet and go, oh, you're a 6 and 4, so I will tear off the IPv4 headers right here and communicate back to the IPv6. Now, the beauty of that is you're doing IPv6 to IPv6 communication through an IPv4 network without using any kind of NAT. All it's doing is recognizing that I'm going from a 6 to 4 to a 6 and 4, 6 to 4 destination, and you're doing it without converting the IPv4 address, and it's all done. That's where I was going, automatically, right? Now you will need to configure this device called a 6 to 4 relay. Right? Which is a device that when it sees this destination, it goes, okay, I'm going to keep that, or essentially regenerate that native IPv6 address on here and send it out here to the IPv6 internet, but that's 6 to 4, and it's obsolete. I know. Well, you wouldn't have listened to me if I told you that from the beginning. 6 to 4 has been circumvented, replaced by 6RD. Why? Well, because think about this. What happens if this IPv4 address changes on the outside of the customer prem? Oh, you have to renumber your entire internal subnet, right? Because the internal subnet is generated from whatever that IPv4 address is. Brutal. So this one was replaced by 6RD, which is very similar. As a matter of fact, it's exactly the same. It just allows the carrier to designate whatever prefix they want. So instead of being stuck in this 2002 : world and being stuck to use whatever this public IP address is, the carrier, the ISP, service provider, that's us, goes in and says, I'm going to designate 5555 : 619, I mean, whatever. They come up with whatever prefix they want, which does not have to relate to this. It's just, it is the designated range of that. And then essentially the 6RD router detects as they are moving from that prefix out into the IPv4 world that this is happening, and it embeds the IP addresses in exactly the same way. So, just think of it, 6RD stands for rapid deploy, by the way, rapid deployment of IPv6. 6RD, exactly the same thing as 6 to 4 without the restraints of having this prefix that we're stuck with. Well, hopefully that helps you feel a little better about this IPv6 world that will soon be upon us. Ironically, North America, who showed the least amount of growth over that 5 year, actually, let me go back to that window that we saw, least amount of growth right here over the 5-year period, is actually further behind the rest of the world now in converting to IPv6. Well, why? Because we've got all the IPv4 addresses, right? We're the ones that allocated them to the other nations of the world, but kept a huge amount for ourselves, so the pressure isn't there in North America. And I'm talking to my United States brothers right now who are scratching their head wondering why on earth we aren't converting to IPv6. Well, the reason why is we're not under the pressure like the rest of the world, who has long since been making the move to IPv6 using a lot of the methods that I've shown you to make it happen and still communicate with this IPv4 internet that is still out there. But we will get there. Come along, US. We will get to IPv6. Well, I hope this has been informative for you, and I'd like to thank you for viewing.